Assalamualaikum and selamat sejahtera. The next discussion is related to the output current equation. From the previous topic, we had discussed how to derive these equations based on the inductive load characteristics and the output current waveform. Now, by using the same approach, we will discuss how to derive the output current equation of the control rectifier. In general, the equation of the output current waveform is also IF plus IN, where IF is the forced response current and IN is the neutral response current. However, based on this waveform, we can see that this equation is only valid when the omega t is in between alpha to beta. Next, we need to find the A constant. In the uncontrolled rectifier, A can be found when the current is equal to 0 and omega t equal to 0. However, based on the output current waveform, we can see that the current is equal to 0 when omega t is equal to alpha. Therefore, the output current equation of the control rectifier can be expressed as follows. To discuss full wave rectifiers with inductive loads, we will refer to a simulation work to understand the operation of the rectifiers. For this simulation, I am using two different firing angles. For the left and right rectifiers, the firing angles are set to 70 degrees and 10 degrees respectively. And if you notice, the firing angle of the left rectifier is higher than the load impedance angle, while the firing angle of the right rectifier is lower than the load impedance angle. Next, we will compare the voltage and current waveforms of both rectifiers. The first and second axes are measuring the input and output waveforms of the left rectifier, while the third and fourth axes are measuring the input and output waveforms of the right rectifier. Now, I will zoom the output current waveform during the steady state condition. Based on the graph, we can see that by using a large firing angle, the left rectifier is supplying discontinuous current to the load. On the other hand, by using a smaller firing angle, the right rectifier can supply continuous current to the load. However, we can see that the output voltage waveform of both rectifiers has a negative cycle. Next, let us consider a large inductive load. From the scope, we can see that both rectifiers are supplying a continuous and ripple-free current to the load. As a result, The wave shape of the input current is a square wave. In conclusion, a single-phase full-wave control rectifier with an inductive load can work under two output current conditions. If the firing angle is higher than the load impedance angle, hence the rectifier will operate under the discontinuous output current condition. Meanwhile, if the firing angle is lower or equal to the load impedance angle, thus the rectifier will work under the continuous output current condition.